Welcome back to the Mechanics of Solids lecture series. In this series of videos, we're looking at examples to compute shear stresses in beams. The next example is a continuation from the previous video. In the first part of the video, we found the allowable load for a maximum shear stress of 130 psi anywhere along the beam, and this was computed to be W equals 60.3 pounds per inch. The next part of the problem, we're asked to compute the shear stress at a specific point in the beam. X equals 42 inches from the end, that would be right here at this location, and Y equals negative 4 inches, that would be 4 inches below the neutral axis. We'll use the formula tau equals VQ over IT. So we need to start by computing the shear force at that location, which if I drop down is going to be right about here on our shear force diagram. Let's start by computing V sub A at the end and then go from there. V sub A equals WL over 2 to a W of 60.3 pounds per inch. The length of the beam given in the previous problem, 23 feet times 12 inches per foot for the conversion factor, divided by 2 is a value of 8320 pounds. V sub H is going to be equal to V sub A, 8320 pounds, minus the slope W, 60.3 pounds per inch, times the length, 42 inches, and that computes to about 5790 pounds. So that's the shear value that we want to go with. Looking at the equation, we also need to compute Q for the stress at the location given, and we need to compute I. Let's start with Q. I'll draw a picture of the cross-section to help guide us. There's the neutral axis. There's the location that we want to evaluate the shear, 4 inches from the neutral axis, and the area we're going to consider to evaluate Q as a depth of 4 inches and a width of 6 inches. The distance of the centroid of that area from the neutral axis would be 6 inches. So we take Q equals Y bar times the area equals 6 inches times 6 times 4, 24 inches squared for the area, and that computes to 144 inches cubed. The I value, BH cubed over 12, we have a width of 6 inches, we have a depth of 16 inches, divided by 12, and this computes to 2048 inches to the fourth. Okay, so putting everything together, tau equals VQ over IT equals 5790 pounds times Q of 144 inches cubed divided by I, 2048 inches to the fourth. And then T. T is the thickness at the location where you're evaluating the shear stress. In this example, it's equal to the width of the beam, 6 inches. This computes to 67.9. Units are pounds, inches cubed on the top, inches to the fifth on the bottom. It reduces to pounds per inches squared, or PSI. There should be a dot there, 67.9. So that is the answer to part B, tau sub H. Last step of the problem, we're asked to compute sigma max, or the maximum bending stress, anywhere along the beam. It's going to occur where the moment is maximized, and it's going to occur at the bottom of the section since the moment is positive. We can compute this as sigma max equals MC over I, where the moment equals WL squared over 8. So let's go ahead and just plug everything in. The moment, 60, the W 60.3 pounds per inch times a length of 23 feet times 12 inches per foot. Is this 23 times 12 inches? I'm going to square that, divided by 8. And then we add in our C value. C is half the depth of the beam, or 8 inches. And we divide by I, which we previously found to be 2048 inches to the fourth. This computes to 2240. Units are, quick check, pounds, inches cancel out there. Inches squared cancels with inches to the fourth, goes to inches squared on the bottom. So we have 2240 psi as expected. And that is the answer to part C. Recall, as before, a quick check, the shear stress is much lower than the bending stress, and so those units, those relative values of bending stress and shear stress make sense. And that completes this problem.